We'll put it on shared screen. Take a minute to do it. Oh yeah, here's it wants to plug in again. It'll take just a minute. Well, I hope you're ready to hear about the Zeeman effect tonight, because we're going to do that. All right, let's see. Move this over here. All right. All right. All right, that looks good. So I've summarized here some of the things that we did in the last lecture, if you can remember back that far. We worked on the fine structure in single electron atoms, especially hydrogen. One of the things we worked out was the energy levels after the fine structure effects are turned on. And this is a summary of the formula we got for it. The energy levels depend on, after turning on fine structure, they depend on two quantum numbers n and j. N is the principal quantum number, and j is the total angular momentum, orbital plus spin. The E squared over A naught is just the unit of energy. It's really the atomic unit of energy, so it's 27 electron volts. And this thing in the square bracket is dimensionless, so if you worked in atomic units, you just drop this prefactor. In the square bracket, you got all this dimensionless stuff. The first term, minus z squared over 2n squared, is the Bohr or electrostatic contribution to the energy levels. It depends only on the principal quantum number, and notably is independent of the L, the angular momentum quantum number, which is a special feature of the Coulomb potential as a central force problem. Because other central force problems, the energies depend on L as well as N. Then we worked out the fine structure corrections after some labor to do it. And here's the formula for it. This formula depends on both the principal quantum number N and also on the angular momentum J. And that's why the energy levels, including fine structure, have a J dependence. However, the correction term still does not depend on L. So of those three obvious quantum numbers, N, L, and J, it's still independent of L, even as it was back in the electrostatic model. All right, so that's kind of the results we got. You may notice that the fine structure corrections are of order alpha squared. Alpha is the fine structure constant, which is about 1 over 137. So this is of order alpha squared, or better would be to say it's of order z alpha squared in comparison to the Bohr levels. And z alpha, as I've said many times, is an estimate for the v over c of the electron. So z alpha squared means that this is a v over c squared correction term, which is what you'd expect for relativistic corrections. All right. So I also made a schematic energy level chart for hydrogen. This is now for hydrogen. These formulas for hydrogen also, although it's not too difficult to generalize them to alkalis. But in any case, for the case of hydrogen, here's what the energy levels look like. This is the schematic diagram here. Here's the n equals 1 level. When you turn on fine structure, it shifts a little bit, but it doesn't split. But notationally, we add a 1/2 subscript to the 1s indication, which applied in the electrostatic model. The 1/2 subscript is the J value, which is 1/2 because L equals 0 and the spin is 1/2, and so you only get a J value of 1/2. For the n equals 2 levels, we've got the 2s level turns into 2s 1/2, but it doesn't split. The 2p levels turn into 2 levels, 2p 1/2 and 2p 3/2. Because if L is equal to 1, since s is 1/2, you get two values of J, 1/2 and 3/2. Now the 2s 1/2 and 2p 1/2 levels have the same n number, namely 2, and they have the same J number, namely 1/2. And since the energy is only dependent in a J, it means those two levels are degenerate with each other. On the other hand, the 2p 3/2 has a different J, and so it has a different energy, which in fact is somewhat higher. And so this is what the n equals 2 levels look like after you turn on fine structure. For n equals 3, the 3s 1/2 and 3p 1/2 are degenerate. The 3p 3/2 and the 3d 3/2 are degenerate, and the 3d 5/2 is sitting up above that somewhat. So this diagram is not to scale. In particular, the distance between n equals 2 and n equals 3 is smaller than between 1 and 2. And maybe more importantly, the splitting here between, let's say, the 2p3 halves and 2p1 half, this is a fine structure splitting. And in the case of hydrogen, this is of the order of alpha squared in comparison to the splitting between the levels of the Bohr model. Alpha squared is of the order of about 10 to the minus 4. It's 1 part in 10,000. So the fine structure splitting is quite small compared to the separation between the levels if you're talking in the case of hydrogen. And so this diagram is really badly not to scale. This means that in the transitions from the 2p to 1s, which is the strongest transition in hydrogen, radiated transitions, there's really two transitions. There's one from the 2p1 half and another one from the 2p3 halves. So this line, the 2p to 1s transition, is actually a doublet, closely spaced by about this 10 to the minus 4 compared to the separation is about 10 to the minus 4 compared to the separation between the main spectral lines. That's why it's called a fine structure, by the way. It's where the name comes from. This alpha squared here becomes Z alpha squared if you're talking about hydrogen-like atoms. And if Z gets to be big enough, that becomes not insignificant. In the case of uranium, Z alpha is about 2/3. So the electron is moving at about 2/3 the speed of light. This would be hydrogen-like uranium. Therefore, Z alpha squared is about a half. And so in the case of uranium, the fine structure, quote unquote, splitting is about half the separation between the 1s and the 2s. In other words, you can't really call it a perturbation anymore. And it means that this whole structure of trying to treat relativistic, quote unquote, corrections as a small correction to a non-relativistic framework doesn't work very well for an atom like uranium. You can no longer distinguish between what you call fine structure and then the gross structure of the atom. They become essentially the same. All right, so those are some comments then about the energy levels of the system. While I'm at it, let me say some things about radiated transitions in the fine structure model. And for that purpose, I'm going to get a different pad of paper, or no, maybe I'll keep this one and just tear off pages. Let's talk about radiated transitions. We'll talk about just electric dipole transitions. You'll recall that they are governed by matrix elements of the electric dipole operator, which is proportional to the position vector. If we're doing this in the fine structure model, and the states that we want to sandwich this around are the eigenstates of the fine structure model, which have quantum numbers n, L, j, and m sub j. And so we'll put them on the two sides here, like this. And one of these is an initial and one is a final state. So let's put primes in the final state to show that it's different. Anyway, this is the matrix element which governs radiated transitions in this fine structure model of, let's say, hydrogen. Now, to analyze this selection rules for this matrix element, let's take the dipole operator, which is essentially the position operator, and let's replace its Cartesian components by the components with respect to the spherical basis. Because if we do, this becomes a T1Q irreducible tensor operator, that is to say with a value of k equals 1. I'll remind you that k equals 1 irreducible tensor operators are nothing but vector operators whose components are expressed with respect to the spherical basis. Now, the position operator x, if I put it in Cartesian form, x vector, is a vector operator. The definition of a vector operator it says something about how the operator transforms under rotations. But here we have rotations which are generated by L. Those are purely orbital rotations. And X is certainly a vector operator under purely orbital rotations because it's a purely orbital operator, vector operator. But if I add the spin to get the total angular momentum J, X is also a vector operator under J rotations because the spin part doesn't do anything to X. So what this means is that we get to use the Wigner-Eckhart theorem twice, once with L and once with J in analyzing this matrix element. Now let me push this up some. In fact, I think I'll tear this page off. All right, so let's move this up some. No. So let's look at what these selection rules are then. So for the L selection rule, it's going to be, since it's a k equals 1, the selection rules are the ones we've seen before. It's delta L is either equal to 0 or plus or minus 1. The zero, however, is excluded by parity in the same way that we've talked about before in connection with the electrostatic model. As far as the J selection rule goes, again, it's delta J is equal to 0 or plus or minus 1, because again, L is a K equals 1 irreducible tensor operator with respect to J rotations. In this case, however, there is no rule to exclude delta J equals 0. There's no parity in analog of parity. And so, in fact, delta J equals 0 is allowed. So these are the basic selection rules then in the fine structure model. There are also selection rules on the magnetic quantum number, but they're not so important for the basics of this picture, because all of these levels that I've sketched here are degenerate in the magnetic quantum number, and so that doesn't affect the energy. All right, so I want to draw in some transitions that are allowed. Notice, by the way, that the 2p a half to the 2s a half is allowed, that because it's a delta J equals 0. The delta L equals plus or minus 1 means that you can go from one of these columns to its neighboring column, but you can't skip more than one. So you can go from 2p to 1s, you can go from a 3s to a 2p, you can go from a 3d to a 2p, but you can't go from a 3d to a 1s. That won't work by electric dipole transitions. So the 3s to 1/2 is another doublet here. It looks like this, and sketch that one in. There's a 3p to a 2s, you can sketch that one, and these are all very similar transitions. If we look at the 3d to the 2p, the 3d 3/2 can make a transition to the 2p 1/2 or to the 2p 3/2. But the 3d 5/2 can only go to the 2p 3/2 because to go to the 2p 1/2 would be a delta J equals 2. So this line 2p to 1s is a doublet, but this line 3d to 2p is actually a triplet. This is what you'd see in the fine structure of the spectrum. All right, this is the basic outline of these transitions in the fine structure model. An interesting thing to note is that the 2s a half level, if you find yourself there, there's no way to get out of it, at least not by means of electric dipole transitions. You can't go straight down to the ground state because that would be delta L equals 0. And what this means is the 2s a half state is actually a metastable state. It lasts for a length of time much longer than other states. The 2p a half state, which has the same energy as a 2s a half state, both states have the same energy, they have radically different lifetimes. The 2p 1/2 state has a lifetime of about 10 to the minus 9 seconds, whereas this is in hydrogen, whereas the 2s a half has a lifetime of about 10 to the minus 1 seconds, in other words, about 100 million times longer than the 2p a half state, even though they have, as I say, they have almost exactly the same energy. By the way, another interesting thing about this fine structure model is the fact that in this model, the 2s a half and the 2p a half states, other states up here as well, but this is the most important one occurs in n equals 2. These two states are degenerate with one another, at least according to the theory that we've been promoting here. Now, this applies actually to all orders in the expansion in V over C, as we find out by solving the Dirac equation. The energy levels, even in the full Dirac equation, still don't depend on L to any order. So the question then is, are these things exactly degenerate? Theorists can go around all day inventing theories, but you got something like this. It's obvious thing to do is to ask an experimentalist to check it out and see if they really are degenerate. During the 1930s, people working with optical spectroscopy believed that there was a splitting between the 2s a half and 2p a half states, which was just beyond the limits of what was visible by optical techniques, but they weren't quite sure. Theorists, on the other hand, thinking about it, contemplating it, believed that if there was a splitting, it was probably due to the interaction of the atomic electron with a quantized electromagnetic field. It's a process which would be described by a Feynman diagram, which I'll sketch for you here. An electron comes in, and it creates a kind of a loop like this, which on one side is the electron and the other side is a photon. In other words, the electron emits and then reabsorbs the photon in its whirl line moving forwards in time like this. This is the Feynman diagram for the process in question. Unfortunately, in those years, all attempts to take that process and to calculate the energy shift that came from it gave the answer infinity, which showed that there was something wrong with the version of quantum electrodynamics which they were using in those days. And also it meant that the theory offered no insight into whether these levels really were split or not. You don't actually have a number, you just have infinity. It's useless. Well, the situation was resolved in the late 1940s by Lamb and Rutherford, who carried out experiments using microwaves and basically established a microwave resonance between the 2s1/2 and the 2p1/2 states. Because the 2s1/2 state is metastable, it's possible to create a population of them that lasts a reasonably long time. And then you can drive it with microwaves and make it switch back and forth between that and the 2p1/2. And by doing that, they proved that these two states, in fact, do not have the same energy. And they, moreover, made a very accurate measurement of the energy difference between them. It turns out to be something like about 1 megahertz in 1 gigahertz in frequency units. So what this does is it gives rise to what's called the Lamb shift, named after Lamb and not Rutherford. Rutherford was the graduate student, so he didn't get any glory for it. And Lamb got the Nobel Prize as well as the name on the effect. So it's called the Lamb shift. Anyway, so let that be a lesson to you in your graduate career. But in any case, if we resketch these, let me resketch for you the n equals 2 levels in hydrogen, including the Lamb shift. It looks like this. If I draw the 2p1/2 level, it's over here. And I'll draw a dotted line where the 2s1/2 level would be if we believe the fine structure model. But actually, it's slightly above that. That's the 2s1/2, because the Lamb shift raises the 2s1/2 level. And then up here is the 2p3/2. And this is, I don't want to make any grandiose claims, but this is not too bad as to being to scale. The splitting of the Lamb shift, which is this splitting here, is on the order of about 1 gigahertz, like this, whereas this splitting is the fine structure splitting, and this is on the order of about 10 gigahertz, about 10 times bigger. Anyway, these are how the numbers came out. Anyway, so there's an interesting episode in the history of quantum electrodynamics, because after the Lamb shift was discovered, theorists really started to think more seriously about this diagram and why is the answer infinite and how do we cure the infinities. And this led to renormalization theory. And the first successful calculation of the Lamb shift was actually carried out by Bethe, and I forget whether it was 47, 48, 49 in one of those years. He actually did the calculation on a train ride home from a conference. In those days, people rode trains, on the way home from a conference. He just knew how to do it after he saw the presentation of the experimental results. All right, anyway, that's kind of the story of hydrogen then, including details like the Lamb shift. And let me just ask, are there any questions about that before I go on?
Professor,
yes.
Can you explain again why transition is modeled by the dipole Hamiltonian?
Because the electric dipole transitions are the strongest ones. So that's mainly what you see when you look at the spectrum. They're the most powerful. They have the highest transition rates. There are other transitions, magnetic dipole, electric quadrupole, and so on. And those are present as well. And they have different selection rules. But they're much weaker. So if you're looking at the spectrum, they're down by, the intensity is down by, powers of alpha. It's typically alpha squared on going from one class to another. So that's quite a bit, actually, you see, in terms of line intensities. Does that answer your question?
So is it like that the electron sees something like some constant electric field, and that's why you use the dipole?
Well, I mean, there are ways of looking at it in terms of the interference between the old and the new wave functions and making a transition, which creates a dipole moment, which is an oscillating charge, which then radiates, at least if you believe, a kind of a semi-classical picture in which the charge density is really the source of electromagnetic fields. There are ways of thinking about that. And then that dipole oscillation is not there if the right selection rules aren't satisfied. So you don't get that radiation. I'm just presenting a rough intuitive picture of what's going on.
Okay,
We'll
thank you.
cover the subject in more detail next semester. We'll actually see where all these different terms come from.
Yeah, thank you.
All right, any other questions? All right, if that's the case, then I'm going to move on to the next topic, which is the Zeeman effect. So the Zeeman effect, as I think you all know, involves the interaction of an atom with an external magnetic field. It has an interesting history. During the 19th century, Michael Faraday, who was a great experimentalist, believed his entire life that there had to be effects of magnetic fields or electromagnetic fields on atomic spectra, but he was never able to find it in spite of many attempts, because it's kind of hard to do. It requires a good spectrometer, and it requires powerful magnetic fields. In any case, the deed was finally accomplished in the 1890s by Zeeman, who got his name attached to the effect. Well, in any case, so for the Zeeman effect, we want to, as I say, place our atom. We'll use as we've been doing. We'll follow by using single electron atoms, mainly concentrating on hydrogen or hydrogen-like atoms. We place our atom in an external magnetic field, and if we do that, then we want to use the Pauli Hamiltonian for it. And so to write that out, to be 1/2m for the kinetic energy, P minus E, this P plus E over C, because Q is minus E, times the vector potential squared, plus the potential V of R, which would be the Coulomb potential for hydrogen. I'll add in the fine structure corrections because we know how to do that now. And then there's a final term, which is minus mu dot B, where mu is the magnetic moment of the electron. This is basically the Pauli Hamiltonian, but with a fine structure added in. Now then, the first thing to do is to say, what about the magnetic field? Let's take the magnetic field to be in the Z direction. So it's B times Z, where B, the magnitude, is just a constant number. It's independent of space and time. For the vector potential, let's take this to be, a convenient gauge is to take it to be 1/2 B crossed into the radius vector R, like that, which if we do that, we get del cross A is equal to B, which we require, of course, for the vector potential. We also find that it's divergence free. It's del dot A is equal to 0. This means that we're working in Coulomb gauge, because Coulomb gauge is del dot A equals 0. And Coulomb gauge implies that as operators, P dot A commutes, P and A commutes, so that P dot A is equal to A dot P. And that means when we expand out the kinetic energy, the cross terms are equal to one another. We don't have to worry about the ordering of those operators. So that's the basic Hamiltonian that we'll use, and the gauge we'll use in the magnetic field, and so on. Now then, it'll simplify things a lot to use atomic units, and I'm going to do that. In atomic units, of course, we have E equals H bar equals M equals 1, where M is the electron mass and E is the charge, absolute value of its charge on the electron. In atomic units, the fine structure constant alpha, which is normally E squared over H bar C, Gaussian units, it's that. If E and H bar are equal to 1, this just turns into 1/C, which is therefore 1/137 point dot dot dot. So the fine structure constant becomes 1/C and vice versa. Likewise, the Bohr magneton, mu B, which is EH bar over 2mc, becomes the E and the H bar and the M go away in atomic units, just becomes 1/2c, which therefore can be written as alpha over 2. And this is also a convenient way of writing the Bohr magneton. Anyway, if we plug this in here, so then this Hamiltonian then, to convert it into atomic units, becomes H is equal to 1/2 of P plus the E over C just becomes a factor of alpha times the vector potential A squared, plus V of R, plus the fine structure corrections, minus the mu dot B. Well, let's take a look at the mu dot B. The mu, magnetic moment, is equal to minus the G factor of the electron times EH bar over 2mc, which is the Bohr magneton, times the spin divided by H bar. That's a standard way this is the way I like to write the magnetic moment anyway. But in atomic units, well, first of all, let's take the electron G factor to be equal to 2, which is a good approximation. And if we do then, and we switch to atomic units, then the Bohr magneton, as I said, turns into alpha over 2. This becomes minus alpha over 2 times the spin S. So, excuse me, the 2 cancels because the GE, it's just alpha times the spin S. And so the minus mu dot B then becomes a plus alpha times the spin S dotted into B. All right. So that's the Hamiltonian in atomic units. Now, let's take this kinetic energy term and let's expand it out into three terms. Just expand out the quadratic terms. Let's call it T0 plus T1 plus T2, where the three terms are the three terms of the kinetic energy. The first one being P squared over 2, the T1 being equal to alpha times P dotted into A. I use this fact up here above to condense two terms into one. But A, as you see, is equal to, can you still see it? It's equal to 1/2 B cross R. And if you put that in there, this can be written as alpha over 2 times the orbital angular momentum dotted into the magnetic field B. Because you rearrange the triple product and you get an R cross P, which is the orbital angular momentum. T2, on the other hand, is equal to alpha squared A squared over 2. And for the given form of A that we've got is 1/2 B cross R with B in the Z direction. This is also the same thing as alpha squared over 2 times, it's alpha squared over 8, excuse me, times x squared plus y squared. It becomes purely a function of position, right? Now, if I were to write out the full Hamiltonian again in a different way, then it's, let me do it. Let me make sure I'm on target here. Let me get this page lined up properly. Write it now, the full Hamiltonian. It's P squared over 2 plus alpha over 2 times L dotted into the magnetic field for the T1. And I'll write T2 as alpha squared A squared over 2. Then we have plus the potential V of R. Then we have the fine structure Hamiltonian. And then we've got the mu dot B term, which is equal to alpha times S dotted into B. All right. So this is our Hamiltonian now, just transformed into atomic units. The next thing we need to do is to order the terms to decide which ones are big and which ones are small. In order to do that, we need to decide how big the magnetic field is. So let's talk about now the size of the magnetic field. The magnetic field, in the first place, we're working in atomic units. So let's call B naught the strength of the magnetic field, which is equal to 1 in atomic units. So let's say B naught is equal to 1 atomic units. The question is, what is that equal to in ordinary Gaussian units? Well, the answer is that it's the unique quantity that has the dimensions of magnetic field that can be constructed out of the constants EH bar and M, the electron mass. And that turns out to be E, electron charge, divided by the Bohr radius squared, A naught squared. In fact, if you look at this is the electric field at one Bohr radius distance from the proton in a hydrogen atom. This is the atomic unit of electric field. So I can call it E naught as well if you want. It's the same thing. E naught and B naught are equal to one another because in Gaussian units, electric and magnetic fields have the same dimensions, which is one of the advantages of working in that system of units. In any case, that's what this is. But if I evaluate this numerically, it turns out to be something like about on the order of, so some factor in front. It's roughly of the order of about 10 to the 7th Gauss. Now this is a pretty strong field because if converted to Tesla, is 1 Tesla is 10 to the 4th Gauss. So this turns into about 1,000 Tesla. Whereas the strongest laboratory magnetic fields that can be created, at least over any significant period of time, are about 10 Tesla. If you use big superconducting magnets, you can get that. So this is considerably bigger than average or even very strong magnetic fields. So the strength of the magnetic field depends on the problem you want to solve, and we need to make a commitment about that. So let's assume that our magnetic field B that we're going to be considering is less than or comparable to, but no bigger than about 10 Tesla, which would be about 10 to the 5th Gauss, which is of the order of about 10 to the -2 atomic units. And if we do that, if we make that assumption, then this 10 to the -2 is coincidentally about the same order of magnitude as the fine structure constant alpha. So that means that in estimating terms here, we can treat the B field, or the vector potential as well, as being of order alpha. So let's go through these terms and see what their order of magnitude are. the p squared in the over 2 in the v of r are order alpha to the 0. They're not small at all. Those are the main things that then govern the structure of the Hamiltonian. The fine structure term we know is of order alpha squared because we saw that when we were talking about fine structure. It's really z alpha squared, but let's suppose it's hydrogen, so it's only alpha squared. So that's down by a factor of alpha squared compared to the kinetic plus potential. The other terms are magnetic field terms. The alpha L dot B has got an alpha in the alpha and another one in the B. So this is of order alpha squared. So does the S dot B, the same thing. It's got alpha alpha there. The T2 term should be counted as order alpha to the 4th because A goes as alpha. So we're going to neglect the T2 term because it's at least 10,000 times smaller than any of the other terms left in here. And if we do that, then to rewrite the Hamiltonian, I'll write it as p squared over 2 plus v of r, which of course is the electrostatic model. And then we'll add to that H fine structure. And then I'll add to that a term I'll call H Zeeman, HZ, where H Zeeman is defined as alpha over 2 times L plus 2s dotted into the magnetic field. This is really just the leading term in the magnetic field strength because the quadratic terms are being neglected. All right. Now, this can be written in a variety of ways since B is equal to its magnitude times the z hat. This is the same thing as alpha over 2 times B times LZ plus twice SZ. Or another way to write it is since alpha over 2 is the same as the Bohr magneton, I had that here somewhere. Here it is right here. Alpha mu B is equal to alpha over 2. Hope you can see that. That means, let me keep track of where I am here. Let me push this off the screen. That means that this can also be written as mu BB, Bohr magneton times the magnetic field strength multiplied by LZ plus twice SZ. So these are different versions of the Zeeman Hamiltonian, which we can consider. We can make use of. I'll just box it like that. Anyway, here's the total Hamiltonian we'll be working with. All right, now this is a convenient way of writing it. Now, to proceed further with this, to see what the effects of HZ are in the rest of the system, we need to consider the relationship between the Zeeman Hamiltonian and the fine structure Hamiltonian. They're both of the same order in alpha, as I just indicated, assuming we count B as of order alpha. But you can make the fine structure Hamiltonian small if you go to higher quantum numbers, move away from the ground state. And you can make H Zeeman small if you lower the strength of the magnetic field. You don't have to be way up here at 100 kilogauss. So there's different ordering assumptions between these two terms. So let me take a look at some cases that we might consider. What I'll call case 1 is the case in which the Zeeman Hamiltonian is much bigger than the fine structure Hamiltonian. In fact, so much bigger that we'll neglect altogether the fine structure Hamiltonian. If we do that, then the perturbation problem we want is an H0, which is p squared over 2 plus v of r, and then an H1, which is equal to H Zeeman. This is just the Zeeman effect being applied to the electrostatic model, as you can see. The eigenstates of the electrostatic model are NL, M sub L, and M sub S. This is the uncoupled basis. We're going to include the spin here. We have to because it appears in HJ. Excuse me, in H sub Z, and the Zeeman Hamiltonian appears right there. And so it appears in the basis states this way, but the spin doesn't affect the energy of H0. All right, so this is the logical basis to use, especially since the LZ and S sub Z are operators appearing in HC, and the ML and MS are the corresponding quantum numbers. These energy levels are n squared fold degenerate. The energies in hydrogen anyway depend only on n, and the L, ML, and M sub S are labels of the vectors inside the degenerate eigenspaces, or of the orthonormal basis vectors inside those eigenspaces. So I said it wrong. The degeneracy is not n squared; it's 2n squared because of spins, either spin up or spin down. That's the degeneracy is 2n squared. So we have to think in terms of degenerate perturbation theory. And at worst, we might have to worry about diagonalizing a 2n squared by 2n squared dimensional matrix. It sounds like a big job. So what is the matrix we need to look at? Well, it would be these basis states in LJ, do it right. It would be in L, M sub L, and M sub S, sandwiched around mu BB, Zeeman Hamiltonian times LZ plus twice SC. And then on the right-hand side, we'd have NL, M sub L, and M sub S. And we make the n's the same on both sides because that labels the degenerate eigenspace of the unperturbed Hamiltonian. And we allow the other three quantum numbers to be different on the two sides. By the way, this 2 which appears here is really the G factor of the electron. I replaced it by 2, but if you wanted to be fastidious, you could write that as G sub E. And that applies obviously also up here in the L plus 2s. That's really what that is a G factor. There's sort of an implicit G factor before the orbital angular momentum, G factor of 1. This is oftentimes a useful way of thinking about how orbital and spin angular momenta contribute to the magnetic moment of a system. The G factor of the orbital angular momentum is equal to 1. All right, now, this Zeeman Hamiltonian here, LZ plus 2 S sub Z, let's look at it. HZ, let's look at what it commutes with. HZ commutes with what operators? Well, the operators that are relevant for this basis are L squared, LZ, and S sub Z. It clearly commutes with L sub Z because L sub Z commutes with itself, and L sub Z commutes with S sub Z because one is purely spatial and the other is purely spin. By a similar logic, the HZ also commutes with S sub Z, the second member here. And therefore, it has to commute with the sum of those two, which is J sub Z. In addition to that, it also commutes with L squared because L squared is a Casimir and therefore commutes with L sub Z. And L squared commutes with S sub Z again because they're different degrees of freedom. So this is some of the operators that HZ commutes with. But notice that it does not commute with J squared. It doesn't do so because J squared is L plus S squared. There's an L dot S in there, and the L dot S has LX and LY in addition to the Z components. It doesn't commute with this. So J squared doesn't work. And so this is an indication for why we should use the uncoupled basis as the preferred basis for the perturbation problem rather than the coupled basis. All right. Now, this matrix element then, okay, so what that means then is that this matrix element is diagonal in the quantum numbers corresponding to LZ, S sub Z, and L squared. Well, that's the L, ML, and MS quantum numbers here. So those primes that I have here can all be erased. I don't really actually need them. And therefore, the matrix that I need to diagonalize for the first order degenerate perturbation theory is already diagonal. And so the energy shifts, i.e. the eigenvalues of that matrix, are just the diagonal elements. That's just what I've got here. So we escape from having to diagonalize any matrices, which is good because their size is pretty big, 2n could be pretty big, 2n squared. Moreover, the diagonal elements are trivial to evaluate because LZ and S sub Z are acting on eigenstates themselves, so they just bring out the quantum numbers. So this is actually a pretty easy calculation, but it's good practice in perturbation theory and thinking about how perturbation theory works. So let me bring this down some. So this allows us right away to write the energy shifts. Energy shifts are equal to mu BB. That's the prefactor out front here. It's actually inside the operator here. And then LZ plus 2SC turns into M sub L plus twice M sub S. And let me box that because this is the energy shifts we get for case 1. We did it in atomic units, but this is how the answer turns out. Now, although this was done in atomic units, this answer, as I've written it out, is actually valid back in Gaussian units. The reason is that mu BB has dimensions of energy, and the rest of this are just quantum numbers which are dimensionless. So it's got the right dimensions, and so it's therefore correct now in Gaussian, or in fact in any other units. And now you can use it in SI units if you want, easily, you see. All right, so let's see what this does to the energy levels. Let's start with the n equals 1 levels. The 1s, let's start with the 1s level. Here, let's do it right. Let's start with the 1s level. This is let me draw it here. This is a twofold degenerate level in the unperturbed system. This level splits into two levels when you turn on the perturbation because of the possible values of these quantum numbers ml and ms. If I represent the energy shift in terms of delta E divided by mu BB, then the upper level goes up by +1 and the lower level goes down by -1 in these units. And if I write the quantum numbers as ml comma ms in parentheses here, the upper one has a quantum number of 0, quantum numbers of 0 and 1/2, and the lower one has quantum numbers of 0 and -1/2. The ground state is an S wave, so it has L equals 0, so ml can only take on the value 0, and this is what you get. You just get this splitting like this. The 2s level is similar. In fact, it's the same story, really. It just looks like this. It splits like this into +1 and -1. But if we're talking hydrogen anyway, in the unperturbed system, this is degenerate with a 2p level, which has actually, it's a total of 6 levels in the unperturbed system. Well, it turns out these split into 5 levels when you turn on the perturbation. So it looks like this. I'll sketch it here. And this ranges between +2, +1, 0, -1, and -2, again in these units of delta E over mu BB, or units of mu BB as the units here. The quantum numbers of the +2 state are 1 and 1/2. 1 times 1 plus 2 times 1/2. You see, it's ml plus 2 ms. Then the next one down is 0 and 1/2. The one in the middle is -1 and 1/2, or it's 1 and -1/2. The next one down is 0 and -1/2, and the one at the bottom is -1 and -1/2. So we have an example here of perturbation theory where a 6-fold degenerate level, when we turn on the perturbation, causes it to split into 5 levels, one of which is 2-fold degenerate and the others are singlets. Actually, these degeneracies I'm quoting only apply to their degeneracies inside the 2p subspace. If you count the 2s subspace as well, you have a degeneracy between this +1 shift here for the 2s and the +1 for the 2p. So that's another 2-fold degeneracy there. Actually, there's a little bit of a lie here because these two degenerate levels with the splitting anomaly 0 actually have a little g-2 splitting. If I put g is equal to the correct g factor, that they're actually even split there. But anyway, this is the picture we get. All right, so this is the basic picture now for this case 1. Now, case 1 is a little unrealistic in the examples I was in the picture I gave you of magnetic field strengths that we were talking about, because the Zeeman, the magnetic field would have to be pretty strong to so completely overwhelm the fine structure that you could ignore it. But it could be done, and anyway, this would be the picture you'd get if you did. There's a second case which is discussed in the notes, and I'll mention it briefly. This is a case again in which the Zeeman term is much bigger than the fine structure term. However, the fine structure term is not negligible. And in that case, what we do is we write H0 is equal to p squared over 2 plus V of R plus H Zeeman. This is the problem we just solved by perturbation theory up here. And then we take H1 is equal to H fine structure, and we add this as a perturbation to it. And this is an interesting additional perturbation calculation, which you should take a look at because it reveals some features of perturbation theory, which are a nice example of features of perturbation theory that are worth at least practicing a little bit on. I'm going to skip it and let you read over that on your own, however. I want to move on to case 3, which is the case in which the Zeeman term is much less than the fine structure term, easily achieved by making the magnetic field weak. So this is the case of the weak magnetic field. And in some ways, this is the most interesting case. In this case, the weak magnetic field case. In this case, the Hamiltonian we want, the H0, is going to be the p squared over 2 plus V of R plus H fine structure. We have to include the fine structure if we want a realistic treatment, because the Zeeman effect is going to be smaller than the fine structure. So the answers won't even be close to being right unless we put the fine structure in there too. So you have to start with this. This is the H0 then. So the H0 is our fine structure Hamiltonian, which I just spent a lecture and a little more on going over. We went over that in some detail. The H1 then is the H Zeeman. The basis for the unperturbed Hamiltonian is the coupled basis. There is no choice of an uncoupled basis. It's therefore NLJ MJ like that. And the energy levels depend on N and L, on N and J, as I explained earlier, but not on L and M sub J. And so therefore the matrix that we need to diagonalize for degenerate perturbation theory is going to look like this. It's going to be NLJ MJ on the left, H Zeeman in the middle, UBB times LZ plus twice SC. And then we have NLJ MJ on the right-hand side, in which I better prime the L and prime the M sub J. Because again, those label the basis vectors inside the degenerate eigenspace of the unperturbed system, which is now the full fine structure model of the atom. However, I think on the previous page, I mentioned that H sub Z commutes with the operators L squared and J sub Z. And those are the operators connected to the quantum numbers L and M sub J. And so therefore this operator, this perturbing Hamiltonian, is actually diagonal in both those operators. And so again, I can remove the primes. And once again, we end up escaping having to diagonalize matrices to do degenerate perturbation theory. We get to just evaluate the matrix elements on the diagonal. It makes it look just like non-degenerate perturbation theory, you see, where you just do an expectation value. And that's going to work here. So this will give us our energy shifts, which look like that. Now, the basis states on the two sides are eigenstates of J sub Z. MJ is the quantum number of J sub Z. So let's write this LZ plus twice SZ. Let's rewrite it as JZ plus S sub Z, because JZ is LZ plus SZ, and there's an additional factor of SZ left over, which is this SZ here, because that'll make the matrix elements of J sub Z easy. It just brings out M sub J. And so this then allows us to, if I can bring this down here, we can now write out pretty easily what the energy shift looks like. Delta E is going to be mu BB, constant factor, multiplied times M sub J, which comes from the JZ here. And then what's left over is the matrix element of S sub Z with respect to the coupled basis. Like this. All right, those are the energy shifts in this case. Now then, so we need to evaluate this matrix element here, the matrix element of the Z component of spin. If you want to do this in a reasonably elegant and efficient way, you need to use what's called the projection theorem. And I'm going to now make a digression into what the projection theorem is and the proof of it. And then when I've done that, we'll return to this calculation and actually evaluate that. So let's now talk about the projection theorem. In describing the projection theorem, I'm going to put it in a general context. The projection theorem is useful in a number of applications. I'm going to put it in a general context. Let's say we have any system whatsoever. And let's say that on that system, we have a vector operator V. Let's call it V as a vector operator by the usual definition. And let's suppose the standard angular momentum basis in a general notation is equal to gamma JM. This notation we've used before for the standard angular momentum basis. Then the projection operator makes a statement about the matrix elements of the vector operator with respect to the standard angular momentum basis. Gamma JM on one side, vector operator V in the middle, and then gamma JM on the other side, in which I can prime the gamma and the M to allow them to be different from on the left-hand side. However, we do require that the J values be the same. That's obviously a restriction on the use of this theorem, but in spite of that, it makes it a rather special kind of a theorem, but in spite of that, it's quite useful in practice, so we'll use it. So what the projection theorem says is that this matrix element is the same matrix element where I keep the states on the two sides the same. So I'll copy them out. But the operator in the middle, V, is replaced by the angular momentum J times J dotted into V divided by the quantity J times J plus 1. Here I'm setting h bar equals to 1. So let me box this because this is the projection theorem. Projection theorem there. All right, that's a projection theorem. Now, my plan with the projection theorem is to, first of all, I'll explain to you why it's called the projection theorem and give you a mnemonic for remembering it. And then the second thing I'll do is I'll outline a proof of it. And then the third thing we'll do is we'll return to our weak field Zeeman effect, and we will evaluate this matrix element. So let's do all of that. So in the first place, why is it called a projection theorem? Well, the way to understand that is to imagine these vectors J and V, instead of being quantum operators, imagine that they're ordinary C number vectors. So let me plot the vector V like this. Here's V. And let's say the vector J has to point in some direction. Let's point it like that. Any direction will work. And let's consider the projection of V onto the angular momentum vector. So I draw the perpendicular down and I get this vector like that. That's a projection. I haven't labeled it yet, but that's what the projection is. Now, what is this projection? It's the same thing as J hat times J hat dotted into V, where J hat is the unit vector in the direction of the angular momentum J. So it's J divided by its magnitude J. And so you can also write this as J vector times J vector dotted into V divided by J squared. And with the J squared, this is all classical, but with the J squared replaced by its quantum value of JJ plus 1, it's the substitution of the original vector V for its projection, which is this, is the essence of this theorem. It says that in a matrix element like this, you can replace V by its projection onto J. That's what this is. All right, so if that helps you to remember the projection theorem, at least explains why it's called that, then that's good. So anyway, that's an element of intuition about that theorem then. Okay. Now, what about the proof of the theorem? I'm going to outline a proof, and let me center this again. So let's see. Before I launch into that, let me mention one thing is that an obvious strategy to proving the projection theorem is to use the Wigner-Eckhart theorem, because this is the matrix elements of a vector operator, which if you change the basis would be a k equals 1 irreducible tensor operator. And the Wigner-Eckhart theorem tells us that this thing is proportional to a Clebsch-Gordan coefficient with a reduced matrix element. This thing in here is another vector operator, because J dot V is a scalar. A scalar times a vector is a vector, and the denominator is just a C number. So the Wigner-Eckhart theorem can be applied there as well. And the projection theorem, in fact, can be regarded as a consequence of manipulations that can be extracted out of the Wigner-Eckhart theorem. It's one of the ways of viewing this. In fact, you can prove it that way. I'm not going to do it that way. I'm going to give you maybe a more lowbrow way of doing it, but it's worthwhile pointing that out. The method I'm going to outline here is based on an identity due to Dirac, and the identity is this: is that if you form the double commutator of J squared with J squared with a vector operator V, that this is equal to twice the quantity J squared times V plus V times J squared minus 4 times J dotted into V. So that's Dirac's identity. And this identity is proved in a straightforward way by using the known definition of a vector operator. It gives you commutation relations in terms of J, and you just grind through it. It takes about 2 pages of algebra, and I would say it's not very illuminating, but when you're done, you come up with this formula. All right. So I'll leave that as an exercise for you to do that, but we'll use the formula here itself in order to prove the projection theorem. So the proof runs then something like this. Basically, all we do is take Dirac's identity and we sandwich it on the two sides with a gamma Jm on one side and then a gamma prime Jm prime on the other side. For the left-hand side, let's work on the left-hand side. Let's let X be an abbreviation for the commutator J squared with V. That's the commutator you see, the inner commutator you see here. So the left-hand side then is equal to the matrix element gamma JM of the commutator of J squared with X. But that's the same thing as J squared times X minus X times J squared. And then on the right-hand side, we have gamma prime J M prime. Okay, that's the entire left-hand side. Now this J squared can act to the left and bring out JJ plus 1. And this one acts to the right and brings out the same JJ plus 1 because we're assuming the J values on the two sides are the same. What's left over is just an X in the middle with a minus sign. So in fact, the whole thing cancels and the left-hand side is equal to 0. Now about the right-hand side. On the right-hand side, we're going to have two terms. So one of the terms is going to be with a factor of 2. It's gamma JM, bra on the left. And then we've got J squared V plus Vj squared. And then we've got gamma prime J M prime on the right. And now we do the same thing. This J squared X to the left and brings out JJ plus 1. This one X to the right and brings out JJ plus 1. Same factor. And both of them just leave a V in the middle. So the whole thing becomes equal to 2 times J plus 1 times the matrix element we want, which is gamma JM sandwiched around V. It's not sandwiched because it's gamma prime J M prime on the other side. The two states sandwiched around V. We get that. This is the matrix element we want for the projection theorem itself, which I'll remind you is up here. Here's the left-hand side of the projection theorem. And here's the right-hand side. All right. Now, however, let me get myself aligned here. However, let's get this out of the way. However, there's also the second term of Dirac's, Dirac's identity, which is right there. And when we sandwich that, what we get is minus 4 gamma JM on the left, J vector, J dotted into V scalar. That's a scalar product, gamma prime J M prime on the right. Okay, so the entire right-hand side is, if I circle this here, this is the entire right-hand side. I made a mistake here. This 2 should be a 4 because we had two terms that were equal to each other. So there's a 4 there and a 4 there. The right-hand side equals the left-hand side, which is equal to 0. So I can cancel the factors of 4, which are common. I can divide by JJ plus 1, which solves for the desired matrix element, brings it over here as a denominator. And if I do that, then what I've got is the projection theorem. There it is right there. Okay, so that's an outline then for the proof of the projection theorem. Are there any questions about that? This is kind of technical stuff, but it's useful for this calculation. All right, if there's no questions, then let's apply it. Here's our energy shift on a previous page. We need the matrix elements of S sub Z. Let me create a little space here. So we need to translate the notation. From the general notation, the index gamma gets replaced by N and L. These are the extra quantum numbers needed beyond the J, MJ quantum numbers. J just gets replaced by J, and the M that we're using in the general notation gets replaced by M sub J, because that's what we were calling it there. And the vector operator V gets replaced by the spin. Actually, we're only going to be interested in the Z component of it, so let's do that. Something else to notice is that in our application, we don't have primes on the right-hand side. The two states are actually the same. That's okay. The projection theorem allows, of course, for the gammas and m's over here to be the same as on the left-hand side. So if we do all this, then this matrix element, N, L, J, MJ, S sub Z, N, L, J, MJ, is equal to NLJ MJ sandwiched around J sub C times J sub Z dotted into the spin S with an NLJ MJ on the right. And this is divided by JJ plus 1. This is an application now of the projection theorem. And now it's easy to evaluate because in the first place, the JZ, you can let it act to the left and it brings out an M sub J. So we get an M sub J here. In fact, let me just outline for this is going to bring out an M sub j here. When I do that, so it takes care of the j sub z. As far as the j dot s is concerned, let's notice that j minus s is the orbital angular momentum L. And if we square both sides, we get cross terms, which are j dot s. And if you solve for them, the cross terms, j dot s, is equal to 1/2 of j squared plus s squared minus L squared. So this j dot s operator, which appears right in here, can be written in terms of operators, which are then acting on eigenstates of themselves. This coupled basis eigenstate is an eigenstate of j squared, s squared, and L squared. And therefore, this operator then gets replaced by its eigenvalues, which are 1/2, we write this way, j times j plus 1 minus s times s plus 1. Let me bring it down. I hope I have a little room there. It's actually plus s times s plus 1 minus L times L plus 1. And s times s plus 1, by the way, is equal to 3/4 because the spin quantum number is 1/2. And so this matrix element then, here, this S sub z matrix element, turns into M sub j multiplied times j plus 1 plus 3/4 minus L times L plus 1 divided by twice j times j plus 1. And that then completes the evaluation of the matrix element that we need here for the energy shift delta E. There's an MJ factor on the first term and an MJ factor on the second term. So if I put those together then, what I get, let's see if I'm getting this on screen here. What we get is an energy shift delta E that looks like this. It's equal to mu BB, Bohr magneton times the applied magnetic field, and M sub j times a factor I'll call G sub L. G sub L then is equal to 1 plus JJ plus 1 plus 3/4 minus LL plus 1 divided by 2JJ plus 1. And as I'm sure you know, this is called the Landé G factor, like that. So let me box that because there's the Landé G factor. And this is the energy shift then, and this weak field Zeeman effect looks like that. All right. Now, this is actually quite an interesting result. And let me explain why. Because it relates to things we learned earlier about spins and magnetic fields and nuclei having angular momentum and magnetic moments being proportional to spin and all kinds of stuff like that. This is being applied to a hydrogen-like atom. Let's draw an energy scale like this. If I have one of the levels E in J of the unperturbed system, and if we plot the energies as a function of magnetic field strength like this, then what this formula shows is that when you turn on the magnetic field, the energy is split according to the magnetic quantum number M sub j. So you get a fanning out of energy levels that look like this. You know, depending on how many, what the j value is, you get energy levels fan out like that. This of course looks just like what happens to a spin like a nucleus in a magnetic field. When you turn on the magnetic field, the energy levels fan out just like that. If I have another level down here with a different value of n and a different value of j, it might fan out in a different way. There's a different value of j, so there's different number of sublevels. It might have different slopes and so on. All right, anyway, but this is the picture you get. And this Landé G factor then is related to the slopes of these levels. Now, if you look at this formula for the energy shift in terms of the G factor, this is the same thing that you'd get for a particle or nucleus that had a magnetic moment. Let me draw it as a vector. Had a magnetic moment which would be equal to minus G Landé times the Bohr magneton times the spin. In this case, we're talking about the spin of the electron divided by h bar. It would look like that. If you had a particle with this magnetic moment, then the interaction Hamiltonian would be minus mu dot b. And then you'd get exactly this formula for the energy splitting. All right. Now, this formula here, which would give the same answer, is showing the magnetic moment being proportional to the spin. The spin, by the way, is the same as a J. The spin really is replaced by J here in this discussion. I should have called it J because we're calling this M sub J here. But it's essentially the angular momentum of the state in question. So this formula, which is being written down by analogy with what happens with spinning particles like nuclei, shows a proportionality between the magnetic moment and the spin. However, in the atom, the magnetic moment is not proportional to the spin. It's proportional to L plus, or it's not proportional to J, excuse me. It's not proportional to J. It's proportional to L plus twice S, whereas J is equal to L plus S. And clearly these operators are not proportional to one another. And so what's going on here is that what's going on in the weak field Zeeman effect is that the magnetic moment, which applies in the full Hilbert space of the atom, is not proportional to the spin, or not proportional to the angular momentum, because of the G factor, because orbital and spin have different G factors. On the other hand, if we restrict it to a subspace of a fixed value of J, a single irreducible subspace, then on that space, all vector operators are proportional to one another, and mu has to be proportional to spin. So on that subspace, this is what we get. In fact, what this shows you is that the Landé G factor, and by implication, therefore, all the G factors, like of the proton, the neutron, the nuclei, and everything else, all those G factors are really nothing but reduced matrix elements coming from an application of the Wigner-Eckhart theorem, which is saying that your restricted operator is proportional to a standard operator, namely the spin. And this is a way of viewing what these G factors are, is they're really reduced matrix elements. Now, on the other hand, if you crank the magnetic field up high enough so that the energy levels of one of these fan outs starts to interact strongly with another one with a different value of J, then you can't use this. And then the simple formula number one isn't true anymore. So mu is no longer proportional to B, not even in the energy levels. And what happens is you're getting mixing between two states of different values of J. And this is roughly why it is that in the classical limit, you find that the angular momentum is not proportional to the magnetic moment in general. It's because you have, in the classical limit, you have huge numbers of levels and they all can be mixed together. Okay, so it's for that reason that I think the weak field Zeeman effect is particularly educational. Okay, that's all I want to say about the Zeeman effect. Are there any questions about that? All right, I know you've been through this before. It's worthwhile thinking about it again. All right, then the last and final topic for the semester is hyperfine interactions. And I'm going to make a beginning on that tonight, and I'll finish it on Thursday. I doubt if it'll take the full hour on Thursday, and if it doesn't, I'll just quit early, unless there's unless there's a lot of questions. I'll answer any questions you have. But anyway, this is the last topic of the semester. So hyperfine effects, first of all, what are they? They're called hyperfine because the energy scale is smaller than fine structure. But physically, they're not at all like the fine structure. The fine structure, you'll recall, is the effects of relativity and spin on the dynamics of the atomic electron. Hyperfine effects have to do with the interaction of the atomic electron with the multipole moments of the nucleus. So here's the idea, is if we magnify the nucleus tremendously so it becomes some kind of a blob like this, and I put a coordinate system in the middle of it with coordinates x, y, and z, you can think of the nucleus as having internally a charge density rho, which is a non-trivial function of position, and also a charge current, which is a non-trivial function of position. And these then generate electrostatic and magnetostatic fields. Electrostatic fields includes the Coulomb field, which is the main field that keeps the atom together, and the current, which produces a magnetic field, which is responsible for, amongst other things, the magnetic moment of the nucleus. So if you have some field point out here, let's call it position vector x like this, position vector to this, you might want to evaluate the electrostatic potential phi of x and the vector potential a of x at the field point. Now, if this were a problem in classical electrostatics or magnetostatics, you would expand, you would commonly expand both phi and A in a multipole expansion. So let me remind you what that looks like. For the electrostatic potential phi of x, the leading term, the monopole term, looks like Q over R, where Q is the total, is the integral over all, it's the integral over the charge distribution of rho of x. It's just the total charge in the charge distribution. But there's a dipole moment, d, and a dipole contribution to the potential, which is d dotted into x over r cubed. And the dipole vector is equal to the integral over the source distribution d cubed x of x times rho of x. The dipole moment, this is classical now. I should emphasize that below this line, I'm talking classical to just to remind you of some basic facts here. The dipole moment vector is basically the charge weighted average of the position vector of the position vector. In any case, this is the dipole contribution to the potential. There's also a quadrupole contribution, which I can write it this way. It's 1/6 the sum on I and j of a tensor qij times another tensor tij divided by r to the 5th power, where tij is a tensor that will appear more than once. It's 3xi(xj) minus r squared times delta ij. It depends on the coordinates x. And this is, as you can see, is a symmetric and traceless tensor. Q I'll define in a moment. In fact, I'll define Q now. Q is the quadrupole moment tensor. It's the integral over the distribution, rho of x, of nothing but tij. Let me just copy it here. 3xi(xj) minus r squared times delta ij. All right. So this qij here is just numbers because you integrated over the source distribution. This tij are functions of x. It's this full tensor that you put in here. Although qij is obtained by integrating tij over the source weighted by the charge density. In any case, this is just basically electrostatics. Likewise, for the magnetic field, the magnetic vector potential can be written as a dipole term, which is mu cross x divided by r cubed, plus a quadrupole term, which I won't bother to write out, plus higher order terms. There is no monopole term for the vector potential because we don't believe monopoles exist. We only have an electric monopole. All right. And the magnetic moment vector mu is given by 1 over 2c, the integral over the source distribution d cubed x of x crossed into the current density j of x. All right, so this is electrostatics and magnetostatics, some basic formulas summarized here. All right, now. So we have electric monopole, electric dipole, electric quadrupole, and higher order terms. We have magnetic dipole, magnetic quadrupole, octopole, and higher order terms. We'll call these in general, I'll call these in general 2 to the k poles. The reason is that if you make a table here of k and the name, you get a lesson in how to do logarithms in Greek and Latin. When k is 0, the name is mono. When k is 1, the name is di. K is 2, the name is quadru. And k is 3, the name is octu. And this corresponds to 2 to the 0 equals 1, 2, 1 is equal to the 2, 2 squared is equal to 4, 2 to the cubed is equal to 8. In other words, the Latin and Greek name is the power of 2 that you see here, and it therefore identifies, in a sense, the logarithm of the k value. I'm choosing the symbol k to represent these names, mono, di, quadro, octo, and so on, for a reason, because it turns out that these various multipole moments are related to irreducible tensor operators of rank k. Let me elaborate on that a little bit. I'm going back to the previous page here. In this classical description of multipole moments here, the Q, the D, the monopole charge, the dipole moment, the quadrupole moment, the magnetic dipole moment, and so on. Classically, these are just numbers which describe the charge distribution. But if this thing is if this thing is really a nucleus, then it's a dynamical system in its own right, and therefore it has a Hilbert space. In fact, we know what the Hilbert space is. In fact, let me say something about the Hilbert space of the nucleus. Let me do it here. The Hilbert space of the nucleus, let me call it E sub nuclear. You know what this is. It's related. It's a single irreducible subspace under rotations. We talked about this in spins and magnetic fields. Tell you what, let's do. Let's write I vector is equal to the nuclear spin. We'll use this symbol to distinguish it from S vector, which will be the electron spin in our atom. So spin like this. The operator I squared, we'll write it as I, it has eigenvalues I times I plus 1 H bar squared. So the nuclear Hilbert space can be thought of as, we write it in terms of its standard basis. It's the span of the basis vectors, which are I, Mi like this, where Mi runs from minus I up to plus I. All right. Anyway, that's the nuclear Hilbert space. Now to go back to what I was saying just a moment ago, these moments in a classical distribution are just C numbers, they're just numbers which describe the distribution. But the nucleus is a dynamical system. It's a quantum system. It has a Hilbert space I was just talking about. And so what that means is that these moments are not just C numbers, but rather they're things you can observe. They're observables that are observables of the nuclear Hilbert space. And therefore, they're, by the postulates of quantum mechanics, they have to be represented by operators on the nuclear Hilbert space. Now, as far as the total charge is concerned, that's a pretty easy operator because the total charge Q just becomes the magnitude of Q times the identity operator on, let me just write this way as 1 on the, let's see, I'm sorry, I didn't give enough room here. The Q, the total charge operator is just a multiple of the identity. Everybody agrees on what that is. The magnetic moment operator, as we know, is a vector operator on that Hilbert space. And because of the Wigner-Eckhart theorem, this is some constant multiplied times the spin, which is I. This is true for any other vector operator, such as the electric dipole moment. This is another constant times I. As far as Qij, which is the quadrupole moment tensor, this by a similar argument is proportional to any standard quadrupole tensor operator, which one would normally choose to be 3iij minus I squared times delta ij, like this. So these are different constants depending on what the moments are. But in any case, this is what these operators have to be. But the point is, these are now operators on the nuclear Hilbert space. So going over to the quantum system then, this multipole expansion means now that the vector potential and the vector potential and the scalar potential, both of them, now become interpreted as operators not only on the Hilbert space of the electron, that's what that is, that's the position of the electron, that's what we're thinking about here for the electron moving in a potential V, but also they are operators on the nuclear Hilbert space because of the Q, which is trivial, the dipole moment vectors, the quadrupole moment operators, quadrupole moment tensors, and so on. Okay. This means that in the quantum description of an atom in which we want to take into account the interaction between the nucleus and its multiple moments and the dynamics of the electron, we have to enlarge the Hilbert space of the atom by forming the tensor product with a nuclear Hilbert space. And so this, of course, enlarges the Hilbert space and introduces new quantum numbers. In particular, the spin of the nucleus comes in. We can also expect that the contribution to the Hamiltonian describing the interaction between the nucleus and the atomic electron is going to involve operators connecting with the nucleus, in particular the nuclear angular momentum, as well as the operators involving the electron. If you look at this just from a classical level, you can understand why the electron is coupled to the nucleus. If I just took this as a classical system, the nucleus is a classical system with some current and charge distributions in it. It's got a magnetic moment. Usually it does. It has a magnetic moment. The magnetic moment is a vector. It means the nucleus has an orientational degree of freedom, even treated classically. It's got a direction in which the magnetic moment points. It has that. And that direction governs the magnetic field, which is produced by that dipole. The electron is moving in that magnetic field, and so it feels a V cross B force from that magnetic field, which therefore depends on the orientation of the nucleus. The electron's spin, of course, has its own orientation and precesses in that magnetic field. However, the nucleus also feels a magnetic field because the electron is orbiting, producing a current which makes a magnetic field at the location of the nucleus. And as well, the electron has spin, which produces an electron dipole magnetic field, which is seen at the nucleus. And so the nucleus is living in a magnetic field produced by the electron, and it therefore precesses in that field. So both particles are precessing in the magnetic fields which they see, as well as the fact that the direction of each of these particles, the precession changes their directions. The direction of the magnetic field determines the magnetic field that the other particle sees. So clearly what we have here is a coupled system of the orientations of both of these particles, as well as the spatial degrees of freedom of the electron, are all tied together in a compound system. And this is the physical essence of what hyperfine effects are all about. I didn't say this, I think, I didn't point this out sufficiently, but the monopole term is, for a nucleus, if you're at all far away from the nucleus, the monopole term is by far the dominant term. And this gives rise to of course, to the Coulomb force, which holds the atom together. So the main features of the orbit of the electron are determined by this term alone. With these other terms here, there are small corrections to the basic structure of the atom. It's these other terms that give rise to what we call hyperfine effects. All right, that's an intro to hyperfine effects. I'm out of time tonight. Are there any questions about this?
Oh, Professor.
Yes.
So you talk about like the dipole moment or so about the nucleus, but the nucleus of a hydrogen is just a proton. So how can it has dipole moment?
Well, we know it does because the proton has a magnetic moment with a G factor of 5.588 and all that. Do you remember that? So how do we know it has a magnetic moment? Well, ultimately the answer is we measure it. It's been measured. This was actually done by Stern, our old friend Stern. He's the first one that did it. He measured the magnetic moment of the proton.
Oh,
so it has a magnetic moment.
I see.
Yeah. The question is, does it have any other moments? Does it have an electric dipole moment? Does it have a electric quadrupole moment? These are questions I'll address in the next lecture. Are there any other questions? If you took some random classical distribution of current and charge, it would have all the moments. Out to infinity. There's a infinite series of them. Is that what we get for a proton? Any other questions? All right. If not, thank you for your attention, and I will do the usual shutdown here. Let's see. Stop share. Stop.